You, Nathan. Appreciate it. Uh, Good to be with you all. I'm sorry I can't be out there on the West Coast or in Hawaii, but I'm here in North Carolina and all set to go. So despite a lot of naysayers, the internal combustion engine is going to be with us for many years yet. It is still the most efficient form of providing power that is on the market and in the foreseeable future. So with that, let me just very briefly, I've been with two engine manufacturers, started off actually as an apprentice with one of the manufacturers in England, and so worked throughout a diesel engine factory and in the service, engine assembly, engine testing, and all the rest of it. It was a lot of fun. I was with that company for 22 years, and they offered me a position with their company in New York, which I thought about very carefully and decided within about 2 seconds that I wanted to go there. So I moved to the US in 1970. And as I said, right now I'm still involved with EGSA. Had the honor of being president of the association in 2012 and director of education before handing the reins over to Nathan. In North Carolina, I'm near a very large lake. This is the closest I can get to Navy experience, but I do have a 28-footer, which I'm very proud of. It's the only one of its kind on the lake. The boat is a little bit old, and the motor needs a rebuild. So that's my form of boating right now. So here's what we're going to be talking about. Some of this you already know from the itinerary that you saw about the program, so I'm not going to spend much time on that, but I will mention at this point that I try not to use too many words on my slides. I use pictures, and that's great for me because I don't have quite so much work to do in preparing a presentation. However, it is putting the onus on you folks to take notes. So you'll need these in the future, I'm sure. But the thing about these programs is that we throw an awful lot of information out at you, more than you can absorb, because as soon as we cover one topic, we're on to the next one. It's difficult to remember it all. Some of the information you'll already know. Some of the information will be totally new to you. And as I said, you're not going to remember it all, but it's, I hope, going to be really useful. And in the future, when go back to the slideshow, you'll be able to look in your notes that you took during this presentation, and you'll also have the advantage of the reference book as well. And that is a book which I believe you folks have, something that will be very useful to you throughout your careers, because it explains in considerable detail the design and purpose of just about every single component that you're going to find on a generator set. And throughout this presentation, you'll see on the lower right box there, whereabouts the topic that I'm talking about is covered in the reference book. So there's another source of information for you in the future. We start off with preparing these presentations with learning objectives, what it is that we think you folks need to know. I'm not going to go through this because the critical time, and the time to go through it really, is at the end of the module when you can do a self-test here. And you can go through these objectives and see if you actually can answer all of these questions here. So Paul finished off by talking about energy and efficiency of generators and of engines, and I'll just go into that a little deeper here. We've got our generator sets, and we start off with chemical energy that is contained in the fossil fuel that we use to power these engines. So the energy in the fuel can be expressed in BTUs, or British thermal units per pound, or a standard cubic foot of the fuel. Now that energy goes into the engine, and we have combustion. And I'll be talking more about that a little bit later. But what happens here is that the fuel is heated, it's compressed, and it is then ignited with either a spark plug or you have spontaneous combustion in the case of a compression ignition engine. It's a little bit like a bullet. So I'll use this analogy for a second. Your bullet is full of explosives, and when it is ignited, it expands, the gas expands very, very rapidly, and it forces the bullet out to the other end. Like that in the combustion chamber. You have a very rapid expansion of gas, it forces the piston down, and what that does, it converts the heat energy that has just been developed, and it converts that into mechanical energy by forcing that piston down and rotating the crankshaft. Rotating the crankshaft, of course, rotates the flywheel. The flywheel is connected to the generator, where we are converting that energy, that mechanical energy, now into electrical energy. And as you know, we've got some magnets, and we're rotating a conductor in that magnetic field and producing the electricity. And then, of course, when it goes through a distribution panel, then we're converting it back into mechanical energy with an electric motor, or light energy with light bulbs, and any other number of forms of energy. And we'll take this one step further. And again, this sort of piggybacks onto what Paul was saying, but we have a generator set here. In this case, it's a 20-cylinder, 3.2 megawatt generator set, so a decent size, but we're putting in fuel, we're having combustion and converting that into mechanical energy and heat energy. So about 25% of that energy goes out through the exhaust pipe. About 25% of that energy goes out through the cooling system. And as you already know, we've got air coming into the generator and being forced out by an internal fan on that generator, and it comes out as heat energy. So these numbers are a little bit, let's say, there's a little bit of leeway in all of them, because the other ingredient here is the radiated heat, which comes up from the engine, and that can be about 5% or so. So don't take the math too seriously on this, but it does give you a guide. The interesting thing to me and to many people is that it's not that long ago when the mechanical efficiency of the engine was about 33%. And it was a general rule, 33% was converted into mechanical energy, 33% went out of the exhaust pipe, and 33% went out of the coolant system. That has changed because the engines are so much more efficient now. So we've got approximately 45%. Some engines, I think, are up around closer to 50% thermal efficiency, which is pretty amazing. And then, of course, we have some loss through the generator because of the heat loss, and it comes out as 40% as electrical energy approximately. I'll just mention here that generally, and with most manufacturers, the power of an engine or a generator is expressed first of all with kW and then the letter E or M to denote whether it's mechanical energy or electrical energy. The heat energy actually can be recovered in some systems, if they're large systems, with cogeneration. And basically, you're putting heat exchangers in the cooling system and the exhaust system to recover that heat and turn the ingredient of that heat exchanger, which is generally water, turn it to steam and then run a steam generator, in addition to the generator that's on the back of the engine. Please interrupt me if you've got any questions as we go along. I was pleased to see that you were fairly vocal and in the last session. And incidentally, it's often questions that come from you folks that that cause us instructors to learn a little bit more. And it happened in the last session that we did with the Navy. I got a question on batteries, and I was not able to answer the question. But with some research and talking to some other experts within EGSA, I was able to get the answer and get back to the questioned us and learned a little bit myself. So that's really useful both ways when you ask a question. Now, the chemical energy that is contained in the diesel fuels, diesel engines are pretty adaptable. They can be run on, generally speaking, kerosene, Jet A, JP5, jet fuel, diesel number 1 and number 2, home heating oil. In the Northeast, we did quite a lot of generator sets when I was working for a distributorship. We installed a number of generator sets that ran off the home heating oil. There's a 275-gallon fuel tank in the cellar, providing heat for the boiler there. So that can be used. Today, we have ultra-low sulfur diesel in most cases, which has a sulfur content of less than 15 parts per million. By comparison, the number 2 diesel that ultra-low sulfur displaced could be over 500 ppm. In some cases, it was closer to 2,000 ppm. So the reason that we've gone to low sulfur fuel is, of course, to reduce the engine emissions, the exhaust emissions. So that's what we're pretty generally using now. Biodiesel, first of all, don't mess with it unless it meets that specification right there. Some say that biodiesel takes more energy to produce than it provides. So there's some questions about biodiesel, but if you're going to use it, I would recommend that you contact either the engine manufacturer or their distributor to find out, A, if it is suitable for their engine, and B, what percentage of the biodiesel can be used with that engine. Don't take a chance, because it has happened, and I've seen it happen, where an engine has seized up and stopped running because of the biodiesel, which was about 90%. And it had the effect of gumming up the fuel injection equipment. So it all had to be stripped down. So be very careful with biodiesel. A better fuel to use is coming on the market now, HVO, hydrotreated vegetable oil. This has no production, really production costs. It's a fuel that is already available. It just has to be blended together, but it's very clean, and most diesel engine manufacturers approve of it. They've all done the appropriate tests and everything. Now, the next one is kind of interesting. I wonder how many of you have heard of biofuel. This is where you take a standard existing diesel engine and feed it natural gas. Sounds a little odd, but it's quite a simple system, and it works really well, and there's some benefits to it. Now, I'll go through these. Basically, it comes in a kit form from a couple of manufacturers offer this, and you can see over here that we've got here we've got a manual on-off valve. The gas is coming in from the left, and this first item here is the on-off valve that allows gas to flow into the gas regulator, which is on the engine. And that makes sure that the gas supply is at the correct pressure and that there's sufficient volume there available to partially run the engine. Then beyond that, we have an electronically controlled on-off valve. And we have the gas supply going to the engine with a mixing device inside it. And there's also a controller. So it's all electronically controlled, and it's going to monitor the system for safety and performance. What it looks like on the engine is this. We've got a Caterpillar here. And so here's the on-off valve, the regulator, the electronic valve, and then it goes into the turbo, and then it's fed from there into the inlet manifold. Actually, it goes through the intercooler. Now, here's the reason. I won't go deeply into the math, but I'll rush through this fairly quickly. So let's take the example of a 250 kW generator, which this one is. Now, generally, generator sets operate at less than their full capacity. So I've taken this running at 80% of the load, And the brake-specific fuel consumption, as published by the manufacturer of this engine, is 0.33 pounds of diesel fuel per brake horsepower per hour. Now, this is a really important sort of formula, if you like, because you can't make a general statement that a diesel engine is going to produce or is going to consume, say, 12 gallons of fuel an hour. It depends on how much horsepower is being taken, and this formula takes that into consideration. So to produce 250 kW, you need 360 brake horsepower out of the engine. 80% of that is 288 brake horsepower at 80% load. And the diesel fuel consumption, we take 0.33, multiply it by 288, divide it by 7 to convert it from pounds to gallons per hour. And that is 13.6 gallons per hour at 80% load, okay? Now, if we start injecting another fuel into the engine, what's going to happen? It's going to be a little bit like being in your car at a steady 50 miles an hour and you want to go faster, so you push your foot down on the gas and the extra fuel will give you the power that you want. In the case of a diesel engine, we don't want that extra speed. What we want is a constant 1800 RPM, 60 Hertz steady out of the generator. And we do that, of course, with the governor. Now, if you add more fuel to the engine, in this case, natural gas, it's going to tend to increase the speed, but immediately the electronic governor, or even an old type of governor, is going to sense that and is going to cut back on the diesel fuel so that it is only running at 1800 RPM, regardless of the fact there's some other fuel messing around in the induction system. So it cuts back. And this system will can reduce the amount of diesel fuel by about 30%. So let's just take this to a slightly different level. Let's say we've got 60 hours of capacity with a diesel tank that's alongside this generator set. So in 60 hours at 13.6 gallons per hour, that's 816 gallons of diesel fuel that's going to be consumed. So with a biofuel system, I'll be conservative here, even though we can go at 70% natural gas. Let's just say it's 60% natural gas, 40% diesel. That's a very dramatic reduction in diesel consumption. 326 gallons versus 816 gallons in a 60-hour period. So that's 490 gallons saved. And we're running at a fuel consumption of about, 5.4 gallons an hour. That gives us an extra 90 hours of running time. This can be really important if there's a regional power failure and you've only got a limited amount of fuel. If it's a hurricane or something else that's blown through, or an earthquake perhaps, you'll find that it's going to take perhaps 3 or 4 days before the logistics of getting fuel from its source to the site of the generator set can be unacceptable. You've got to keep running. So this is one way of doing it. It does have an implication on the emissions, which may not apply to you folks, but in the commercial field, it is necessary to check with the authority having jurisdiction, the AHJ, to make sure that the reduction in exhaust emission, most of the exhaust emissions, does not counteract any regulations. The carbon monoxide will increase, and that can easily be fixed by the addition of an oxidation catalyst. So overall, there are places where that is very useful. As I said, this is just very simply a kit which can be added onto an existing engine. Some generator set manufacturers offer this all readily installed. A quick pause for questions. Jump in if anyone has a question here. Briefly on fuel storage, the majority of generator sets are installed on top of a fuel tank. These tanks are double walled. They meet UL specifications. double-walled, with the capacity generally of being able to hold 110% of the fuel tank capacity if there should be a leak. They'll also have a leak detection device as well, so that if fuel does leak out of the primary tank, there's a message appearing somewhere that someone can act on and put a stop to that. They come in different shapes and sizes, and practically some of them look kind of crazy because the fuel tank is almost higher than the generator set that's sitting on top of it. In the center picture there, you can see that there is a large capacity fuel tank in addition to the one under the generator set. Prior to installation of the enclosure, that is a big fuel tank right there. Now, if you have a remote fuel tank, you'll probably have a day tank available with it. So here on the left is our main storage tank, and fuel is sucked up from this tube here, this pipe, into a pump set, and from there, the fuel is pumped up to the day tank. The generator set will draw fuel from this with its own internal pump and come into the generator set. And because diesel engines recirculate some of the fuel, it's used for cooling of the injection system, there'll be a return line which comes down and goes back into the tank. The day tank will have an overflow, and that will go back to the main tank. And then we've got our controller right here. And here's an up close look at a day tank. And again, this has an enclosure around it so that if there's any leakage here, it'll be contained and will not spill. So all very simple. But sometimes things go wrong. And what can go wrong? Well, first, and not unusual, is that you can get contamination during transportation. First of all, you don't know how long that fuel has been stored. You don't know the condition of the bulk storage tank where it was. Also, you don't necessarily know what was inside this tank here that's got your fuel inside it. What was in that tank before, and did they clean it out properly? Was there any residue of that previous shipment? So that can give you contamination during transportation. Fuel leaks can be really expensive. We had an employee at one of my places where I worked. He got home after work one day and opened the door, could smell gasoline, which scared the heck out of her, of course. She went down to her basement, and the generator set, which she had storing in there, a little portable, had leaked some gasoline onto the floor. He was very worried about explosion, so she immediately called the fire department, and they came along with another environmental agency, and they presented her with almost a book. It was about 1.5 inches in thickness of all the forms about her spill and what she had to do about it. It was very expensive, and that was for about a half-gallon spill of gasoline. So if you get a spill of diesel fuel, it can be really, really bad. Water in the fuel tank, usually due to corrosion caused by condensation in the tank. Algae formation, more so, we're seeing a lot more algae formation with the use of ultra-low sulfur diesel and bacteria fungus as well. So this means that the fuel does have to be checked. And here's what you might find at different layers. Bacteria sludge is the heaviest, will go down to the bottom, then water, then biomass and algae and stuff. And then you got your diesel fuel, and then you got your air. So it can get ugly if you don't check it. So check your fuel source. Be careful about biodiesel. When you take a fuel sample to get it analyzed, take 3 samples at the top of the fuel tank, in the middle of the tank, and at the bottom. After you've had the delivery, if you can, just let the fuel settle for as long as possible, so all or any impurities in there are going to go down to the bottom. Check the condition of the fuel filters coming out of your main fuel tank. That's something that many people forget. And then finally, there's fuel polishing. Go into that in just a minute. It seems kind of odd that you can polish something that's liquid, but that's the expression that's used. There's one little tool that can be used sometimes to check what's at the bottom of the tank. And it looks like this, a little spring-loaded thing, so you can push it through a hole in the fuel tank down to the bottom, and it'll bend and it'll pick up some garbage if it's down there.
Have question.
Yeah.
Okay. Can you go back to the slide with the large fuel tank?
With the fuel tank?
Yeah, the one with the large.
This one?
No, back one.
Ah, that one.
See, on the top. See, with the really large fuel tank like this.
Yeah.
Do we consider the clearance? Because when you stay on the top of the fuel tank to make the maintenance, anything is we need to consider the clearance.
Oh, the clearance between the generator and anything else and the tank itself?
No, because when you step on the tank for the maintenance, right, or something, do we consider the clearance?
That's a very good question. Usually what happens at installation is that there will be a separate floor above the fuel tank. So you're not actually stepping on the fuel tank.
Yeah, but because if you want to step on the fuel tank, it need to be clearance from the generator. It's about 3 or 4 feet, something. But I don't know if the tank is large enough the clearance for you step it on, because you cannot stay on the floor to maintenance. You have to step on the fuel tank to maintenance.
Yeah, usually, or in many cases, there is a steel cover over the fuel tank, so that you're not actually stepping on the fuel tank. And then there'll be openings there, so you've got access to the inspection and filtering system. Does that help? And you see there is some clearance between the generator and the fuel tank there. It's a matter of inches, though. One of the reasons, another reason for putting a plate above the fuel tank is that there is a gap, because the outside of that fuel tank is actually part of the containment system. So you don't want to drop anything down between the fuel tank and the outside edges of the supports there.
So maybe in this case, we need to put the control panel or something in the back or on the head of the transformer or something. I don't know if we can put on the side, because it's gonna be affect to the clearance.
Yeah, as I said, it'll be on either on the floor, which is above the fuel tank. It can be mounted on that, or a separate frame going across the fuel tank to support anything that's heavy. Does that help? I sense a little bit of doubt here.
Yeah, I don't clear, but it's okay. I just set the question only.
Okay, but it's a good question. And as I said, usually there is a steel plate that's running the full length of the fuel tank, so that you don't get anything dropping down on it.
Okay.
All right. Thank you for the question, though. So fuel polishing. What happens here is we suck up fuel from the lowest part of the fuel tank, and it should be, with a bit of luck, it'll be at a very slight angle. So you're going to be bringing all this up into the fuel polishing system, which is basically a pump with a filter. or a couple of filters, and it will get rid of it'll capture all the sludge, and eventually it will circulate all of this fuel and return it back into the tank. One of the important things here is that when this is done, you want to make sure that the suction point is at the opposite end of the return point. So you do get all of this fuel going through the system. If you had them close together, of course, you might just be cleaning up this section on the right here and not the full fuel tank. One of the things that we want to be careful about is the amount of moisture that's in here. Of course, we've got a vent here, so we will get moisture at the top of the fuel tank, and that can cause corrosion, and it can cause moisture getting in there. And the moisture is something that we really need to avoid. So all engines pretty much have a fuel water separator. And what this does is it takes fuel in here on the right. The fuel travels down, and it comes to, it's like an umbrella almost. This is a circular piece, and it's got little channels cut onto it so that it will actually cause the fuel not just to drop down, but to have a slight circulation to it. As it drops down, water being heavier than fuel is going to come down and go to the lowest part of this water separator. It comes through fairly slowly, and obviously it's sized for the engine's fuel flow. So all the water will come down to the bottom here. The rest of the fuel will travel up, go through the paper element, fuel filter, come back down to the outlet and into the engine's fuel system. On the smaller sizes, there may be a glass bowl, a plastic bowl, and you'll actually be able to see the accumulation of any water or gunge and dirt and stuff down here, and you can simply drain it out, which is really handy. So we have to be really careful about this, folks. We do not want water in the fuel to get to the engine. Can anyone tell me what is likely to happen? Has anyone seen this happen, where there's water has got into the engine? Do you know what happens?
Well, I'm no mechanic, but just throw out a couple of gas there, probably rust or engine seizing.
Okay. Yeah, that can be, actually that is a pretty good answer. The reason that you can have the engine seizing is because when that water reaches the injector, it basically turns to superheated steam, and it expands very rapidly, and it can blow the tip off the injector. Now, when that happens, you've got little bits of metal that fall down on top of the piston, go between the piston and the liner, the cylinder liner. It'll scrape that up and down, and you can have raw fuel coming out of the injector because it is just basically blown apart. And it can cause a seized engine. And then the other engines, the other cylinders are going to have to do the work that this one was doing. And so they're all working harder just to keep that 60 hertz output from the generator. So it is a thoroughly bad thing and an expensive thing to happen. Nearly all engines have an automatic shutdown. So if they detect water in the fuel system, they're going to shut the engine down before it does some serious damage to the engine. You may think that we're only concentrating on diesel, but there are almost as many natural gas generator sets around as there are diesels. So here's some of our gas fuels. The thing that you will see right away is that with the energy content, the British thermal units per standard cubic foot, so that volume is adjusted for the temperature, standard cubic foot. Propane has got the highest energy level per standard cubic foot, and next we have natural gas, and then all the others follow behind it. Now, there are reasons why we would use some of the other fuels. Wood gas is really pathetic on its output. If you had a 100 kW generator set and you run it on wood gas, you're probably going to get about 25 kW out of it. But if that fuel is free and you're running the generator set for a long time, it may be worth it. You're just going to have to oversize it for the capacity that you want. Biogas is a little bit better. Landfill gas, that is not very good energy-wise, but it does have the advantage of being free gas. And many landfills are taking that gas, which naturally comes from any leaching field. Instead of flaring it, they can capture it, put it through a filter, and run an engine on it, like this Jenbacher engine here. So that will give them enough fuel to power their own facility instead of buying it from the utility company. And in many cases, it will produce more electricity than they actually need, so they can sell the surplus back to the utility company. So it's a pretty good thing to do. They need a larger engine to produce the normal amount of power that than the generator set would produce if it was running on natural gas. So let's just look at the fuel system for a natural gas engine. We've got the gas source. It may be a pipe, it may be a tank, and we have a primary regulator to get that down to a usable pressure. We'll have a manual shutoff valve. Then we'll have a flexible connection to the generator set and a fuel solenoid on there. Then an engine-mounted regulator to control the pressure and make sure we got the right flow. And then either a carburetor or a fuel injection system. One of the things that we have to be aware of when we're talking about a natural gas generator is that when you shut that generator set down, it should be designed in such a way that the gas will shut off before the ignition system. You don't want the engine turning over for a while and still pouring gas into the engine, which won't ignite because the ignition system has been shut off. And you'll get unburned gas in the exhaust system. And if that exhaust system is still hot, then bad things can happen if it ignites. So we have talked about the energy, about the fuels, about fuel storage, and now actually we get to talk about prime movers. So let's get into that. And I feel somewhat privileged here because what we're going to be talking about is something that you can see, touch, smell, feel, unlike Paul's session on basic electricity or on generator alternators that you can't see what's happening there. Okay, any questions with what I've talked about previously? Okay, so what is a prime mover? Can anyone define a prime mover? I'm not looking for an example like an engine, but what is a general term? What is a definition of a prime mover? And it is rather specific. Okay. Well, we got a whole section on prime movers. It's a machine that converts potential kinetic, chemical, or thermal energy into mechanical energy. So the end goal here is the mechanical energy. And we've got a number of ways that we can get that conversion happening. Okay, let's have some examples of prime movers. knowing the definition. This is your opportunity to contribute here, guys. Give me an example of a prime mover.
An engine.
Thank you. Yep, that's definitely one. What else? What other prime movers are out there?
How about a pump?
Yep. Yep. That can certainly be one.
Windmill.
Yes, thank you. Definitely. And along similar lines, actually one of the earliest prime movers. So wind was one. Windmill, definitely a prime mover. There's another one that's somewhat similar.
I don't know the term for it, but using water to sort of convert water movement into mechanical energy.
Thank you, Clayton. Absolutely right. Yep. Yeah, this was one of the early ones, wasn't it? We'd have something like this, where water is dropped on a big wheel at a fairly decent height that converts the kinetic energy of the water into mechanical energy as the wheel turns under the weight of that water. And then inside, we've got a grist mill or something else that is being used. So that was one of the early ones. Today, we've still got that same form of energy and prime mover being used. We've got water storage here, and we go through the penstock to a turbine down here. The vertical shaft turns a generator, converts. So we've got the conversion of mechanical energy here and the conversion to electrical energy here, and then it goes out to the grid. And that's basically the turbine and the generator on a huge scale. So I know we've got some problems in different parts of the country where there is hardly enough water to run that turbine. Okay, the other one you mentioned was windmills. I would not mind being at the top of that. Generally very clean energy. So we're using the power of the wind to give us the mechanical energy that we want. Occasionally things go a little bit wrong, and how do you put that fire out, huh? You cannot get a hose up there. The fire department can't do anything to help. But here's how it works. Basically, you've got a wind vane here on the far end. So that is going to send a message to the controller here, which will operate this yaw drive, and will make sure that the windmill is facing the wind. We've got an anemometer, measures the wind speed, and that will adjust the pitch. And then we've got a brake here so that we can shut everything down if the wind gets too much, or if they're going to do some maintenance. So that's another prime mover. Here's another one, the steam engines. This was invented well over 100 years ago, way before the diesel engine or the internal combustion engine, using the power of steam. And it's it's a reciprocating engine, but instead of being internal combustion, it's external combustion, because the boiler that is producing the steam is not a part of the engine, it's somewhere else. And then internal combustion engines. And I'll include gas turbines there because they are internal combustion engines, and they are also used in power generation. So that is relevant. So with all of these, or the last prime mover, the internal combustion engines, and generally, what is essential for combustion? The three things that we have to have for combustion. What are they? Come on, we're going to light a fire here. What do we need?
Heat, oxygen,
Oxygen.
and
Heat, oxygen, and one more.
fuel.
Thank you. Absolutely. Very good. Thank you, guys. Appreciate it. Okay, yeah, take any one of those away and the fire goes out. And there were some old engines. I don't know if any of you are familiar with the Detroit Diesel 71 series, but it had a tendency to run even after it had been shut down. And the only way to stop it from running was to shut off the oxygen going to the engine. Going to talk for a couple of minutes about gas turbines. There are four types basically: turbojet, turboprop, turboshaft, microturbines, and auxiliary power units. The last two are the ones that we're really interested in. So just to make sure everyone understands how these very simple machines work, here's how. Put in air, add some money, and you get noise out the back end, okay? But seriously, it's like this. We have the intake here. Air comes in. These vanes here are compressor blades. And as the air comes in, it is forced to a smaller and smaller space. So you're increasing the pressure as the air comes in across the cool section here. And as it gets compressed more and more, it gets hotter and hotter. It's like pumping a bicycle tire. And you know the effect of that. When you have pressure, you get heat. So you've got oxygen and you've got heat coming into the combustion chamber. Now you add the fuel, you have combustion and a very rapid expansion of those exhaust gases. It goes across the turbine and comes out of the other end with a considerable amount of thrust. And this turbine wheel is connected to the compressor shaft. So that is what powers the compressor. Very simple, basically one moving part, a bunch of small parts, injectors and so forth. So very simple, very reliable. As far as we're concerned, the interesting part is what can we do with it in the power generation industry? And there are many uses for them. The one on the top right is a microturbine. Typically, they're used for large power generation systems. Utilities use them for providing additional power when their demand on electricity is greater than their capacity to generate. And they'll fire up a gas turbine unit to provide power at the peak period. They're called peakers, by the way. And we have some ships. Actually, a lot of ships are powered by gas turbines, especially on the military side. So I'd like to just talk about the advantages of gas turbines as it relates to generator sets. And this is where I'll ask your participation. I'll give you a minute just to write down what you think would be the advantages. Now, I would suggest you write this down. So what are the advantages of a gas turbine versus any other source of prime mover?
Is it efficiency?
Yep, they are efficient.
More efficient?
Yeah, good response.
Also less heat output? Wasted heat?
Yes, to a point, but that heat can be recovered and frequently is recovered, which makes them really efficient.
The air pollution?
Yeah, generally they're very clean, and it depends to some extent on the fuel that's being put into them, but they are relatively clean, and it's easy to clean up what does come out. Usually a simple oxidation catalyst will clean up the exhaust, so it is super clean. Thank you. Good response. Well, you got the important ones. High efficiency heat recovery from the exhaust. That's called HRSG, heat recovery steam generation. So what can be done here? Excuse me. Okay, can you still hear me?
Yeah.
Yes,
still
we can
hear
still
you.
hear
Yes,
you.
we can.
Okay, thank you. All of a sudden my AirPods sounded a little different, but good. Okay, yeah, so you can recover the heat from the exhaust and convert it to steam and run a steam turbine. They're small in comparison to a similar size or similar output internal combustion powered generator set. Reliability is great. You know, you've got one moving part. It always amuses me on a plane when there's a delay, they say we've got a mechanical issue. It's usually an instrument or something else. It's very seldom the engine that's causing a problem. They're ideal for peakers, as I mentioned, and they're very smooth. There's almost no vibration at all from a generator set. And you can see here we've got 1.1 megawatts of gas turbine generator set being put into a rental truck. And here it's being another one is being pulled by a Chevy Suburban. You cannot do that, I guarantee, with a 1 megawatt diesel or natural gas generator set. Okay, so those are the advantages. How about on the other side? What are the disadvantages of a gas turbine for power generation? Why don't we use them more?
How about load change? Is it harder to recover for load changes in load?
Yes, absolutely. And this is a killer for many installations where gas turbine could be considered, because of the fact that the rotation of the turbine is not fixed. It's variable. So if you have a varying load, you're not going to get the fast recovery that you would get with an internal combustion engine that's got a governor that can very rapidly respond to any RPM changes. And you will not get a gas turbine being able to take a block load, in other words, 100% load in one shot. That can't happen. So where they are suitable is where you've got a constant load requirement, and that is not an issue. So interesting that you should say that. Of all the schools that I've done, I frequently do not get that as a response, and if I do, it's usually towards the end after all the other disadvantages. So well done on that. Thank you. Okay, anything else? Any other disadvantages with a gas turbine as a prime mover for a generator set?
I think the size maybe gonna be bigger.
Actually, they're going to be a little bit smaller. They have a lower footprint than the similar size internal combustion engine.
Oh,
You may get a little bit of extra size on the support equipment for it, though.
Don't you need like another prime mover almost to start the turbine up and run it?
Yeah, you could. There's a number of ways they can be electric started if you've got the right system, of course. They can. I think they can be started by compressed air. There's a number of ways of starting them, but it's not just like you go out and get a 24-volt starting system.
I don't know, but how about the maintenance?
Yeah, maintenance is going to be more expensive, isn't it? Because
Yeah.
you need special technicians to handle the precision parts and the special materials that you've got. And that brings up one other item as well. The gas turbine is an expensive piece of equipment. You know, it's using titanium and very high precision parts with all those little blades inside there. Also, they are slow starting compared with an internal combustion engine. And the first answer that you gave me, core transient load acceptance down the bottom there. But just look at this. Here we've got a Wärtsilä, which is a big engine. This is a big power plant engine. It takes about 2 minutes to get that started and get it up to temperature so it can take load. Then we've got here the different gas turbines. So 9 minutes is about the fastest that you can do with a small gas turbine. And for many installations, that is just not acceptable. You know, if you've got a standby or an emergency generator set, you don't want to wait 9 minutes, maybe 9 seconds. So this just isn't going to cut it. And for emergency generator sets, and here we're talking about generator sets that are providing power for the support of life or something critical. Hospitals, healthcare facilities, emergency services will require the NFPA 110 on the commercial side. And it has to be able to start, it has to be online within 10 seconds of the utility power failure. Okay, so moving on to internal combustion engines. And maybe now would be a good time to take a 5-minute stretch break. So we come back just before 10 minutes, just before 10 minutes to the hour. Okay?
All right, well, we will be back at 48 after.
Okay, folks. Okay, so reciprocating internal combustion engine is often referred to as RICE.
Michael, before we get started, you do have a question.
Okay, go ahead.
Is there still an EPA restriction for underground fuel tank storage?
There are codes and standards for underground fuel tanks. I think it depends on more on a local level. I'm not sure if it depends if there are federal regulations. I will find out and get back to the questionnaire on that.
Thank you.
Okay, thanks for the question. That's a good one too. Okay. So we've got a couple of different types of internal combustion engine. Of course, there's spark ignition, gaseous fuels. I'm not going to get into the small portable sets. So we're talking about natural gas, propane, LPG, and the rest of them. And then, excuse me. Okay, there it is. And then compression ignition for the diesel engines. And these internal combustion engines come in all different shapes and sizes, from that actually has a piston inside it, and it is compression ignition. For model aircraft, I think. And then at the other end of the scale, we have something like this. 108,000 brake horsepower. And you can see over here, let's see, get my little laser pointer. People walk along here so you can see what size we're talking about. This is a marine engine, so it is large, very large. This is the kind of engine that they would have in container ships. So let's just go through some fairly basic stuff here. We'll start off with the crankshaft. We've got a connecting rod connecting to the piston in the combustion chamber, which is the area above the piston. This is a cylinder that it goes inside. And we have a carburetor. We have air coming in across the carburetor, drawing fuel, in this case gasoline, out of the carburetor. So we've got a mixture at this point of fuel and air or oxygen. The inlet valve is open, so as this piston is going down, it's creating a slight vacuum in here, and it draws in this mixture of air and fuel into the combustion chamber. The piston comes down to the bottom part of its stroke, and as the crankshaft rotates, it starts to come back up again. Now at this point, the inlet valve will close, the exhaust valve is already closed. So what we're doing here is compressing this air-fuel mixture. And just before it reaches top dead center, we're going to provide the heat. We got a little bit of heat from compression, but we add extra heat with a spark plug. Then we have pretty much instantaneous combustion of that fuel, which causes it to expand very rapidly, and it forces the piston down on the power stroke. So this is a money stroke right here. This gives us a mechanical energy. And then the inertia from the flywheel continues the rotation, so the piston starts to come back up again, at which point the exhaust valve opens and it forces all the spent exhaust gas out through the exhaust system. And these valves are operated by a camshaft. It provides a very good seat right here, so it doesn't allow gas to go through. When the cam rotates, then the spring here will cause this to shut down. And that's basically how it works, but let's look at it a slightly different way. Here again, we've got the intake.
Why do they call it four-stroke?
Good question. Bear with me just a second, because here it is. Your question is very timely. So, stroke one, the piston is coming down, drawing in air. And as it comes down, the intake valve will close and the piston will start to come up on the next stroke, which is the compression stroke. So now we're compressing that air, that oxygen, up towards top dead center, and just before top dead center, in this case, we're going to inject diesel fuel or light the spark plug, if that's what it is. And that will force the piston back down on the power stroke, shown right here. So the piston is now coming down, and then the inertia carries it back up again with the exhaust valve open, and it sends the exhaust out on the exhaust stroke. So there are 4 distinct strokes there. So what you can see here is that as the engine rotates, it's only firing once in every 2 rotations. So it is in fact we got 4 strokes. I've seen it referred to by some fairly knowledgeable people as 4 cycle. It's not 4 cycle. It's a single cycle with 4 strokes in it. Okay, so it's so that is how it works. So intake, compression, power, and exhaust are the 4 strokes. Some people prefer to remember it as suck, squeeze, bang, and blow. 4 distinct strokes. And that's how it works. Let's look at it as, again, in a slightly different way, because this is important. We depend on internal combustion engines, and whether it's spark ignition or compression ignition, they all have the same 4 strokes. So in this case, the inlet is here, and here inlet, compression, power, and exhaust. Inlet, compression, power, and exhaust. And we got the piston. The piston has rings on it to prevent these hot gases from getting down into the crankcase. We got a wrist pin here holding the connecting rod, and the crankshaft is rotating. 4-stroke CI, compression ignition. In other words, there's not a spark plug on this. We're injecting fuel. And the way that works is, and I'll describe it in a little more detail a bit further along, but the objective here is to get that diesel fuel, we call it atomized. It's almost like a vapor by the time it gets through that injector, so it will combust very easily. You can take a cup of diesel fuel and put a match in it, and the match will go out. It's only when it's atomized like this, or it gets really, really hot, that it's going to ignite. So that is the 4-stroke. Now, when James Watt, and he's a guy who whose name we borrow for power, when he invented the steam engine, it was totally revolutionary. There was nothing like it that could produce power like that other than the horse. And now he needed to compare it to some known entity in order to measure the size and give people an idea of the size of an engine and what it would do. So he figured out, or decided pretty much, that a horsepower could be related in terms of the work capability of a horse. So power is work capability over time. And I don't know if Paul went into this earlier, but 1 horsepower is equal to 33,000 pounds-feet per minute, or divide that by 60, that's what you end up with. So that is power. Torque, on the other hand, is the turning effect. And I think I can best describe that by putting it into everyday terms. We've all had the misfortune of cutting grass, I'm sure. So that little 3.5 horsepower engine that's sitting on top of the blades, which is the working part here, normally you've got that running at fairly high speed, and the engine has a capability of 3.5 horsepower. Now, where it falls flat is when you start trying to cut some wet, thick grass, and the engine starts to bog. Now, that engine still has 9 horsepower available, but not at the lower RPM. But what you do have is the torque. And in this case, you don't have a lot of torque available, but it will slow the engine down, and you'll detect a different note on it as you start cutting the tough grass. So this is a power curve by one of these manufacturers, 3.5 horsepower. So it is, the horsepower available is very much dependent on the RPM. Now, if you could keep this engine at full RPM, then you'd still have the 3.5 horsepower, but you don't have that much torque. And torque looks something like this. You get the maximum torque at much lower RPM. So this is the turning effect. If this was further down here at this level, then you wouldn't seem to have as much turning effect or much power. You can notice on some vehicles now, particularly diesel vehicles, that you don't need to change, or the transmission won't change its gear as often as it would with an engine that had less torque. And we can look at a power curve from Caterpillar. There's their C15. Here's their power curve. Goes up to, let's see, 500 brake horsepower. It won't do more than 500 brake horsepower beyond 1600 RPM. And then at this point here, that's where the governor cut kicks in, and you can't rev any faster than that. But the torque curve, on the other hand, comes up and starts at 1000 RPM, and it peaks there and holds it. So torque is a fairly important ingredient. So just a summary again, power is the work capability of an engine. Torque is a turning effect. There are various horsepower ratings that you might see in specifications, from just straight HP, more likely to see that on a gas engine, brake horsepower. Paul went into this quite a bit. I've seen a lot of generator or engine manufacturers that quote brake horsepower for a complete unit, including the radiator. So you need to read the fine print to see if the BHP that's quoted with the engine includes the radiator fan. And it's a very good point. It does need checking. On a generator set, certainly it includes everything that is required to run it. KW is another unit of power. Brake horsepower and power and KW are directly related. The difference is we're talking about mechanical KW, not electrical KW. The Society of Automotive Engineers has its own horsepower rating, and that was used certainly years ago, mainly as a sales tool. They wanted to be able to rate car engines and having more horsepower often than they really did. So they'd give it an SAE rating. ISO, International Standards Organization, and DIN is a German standards organization. But generally, we're talking about brake horsepower and kW. Most engine manufacturers will be quoting both. You'll see brake horsepower and kW. Now, kW on the engine manufacturer's list is kW mechanical, not electrical. Oh, just going back, page 682 in your reference book gives you a little more information on that. And just to emphasize, HP and VHP are not necessarily the same, so you can't make that assumption. So here's the relationship between between brake horsepower and watts. One brake horsepower is equivalent to 746 watts mechanical. So you can do a direct conversion. So you can say watts is a tiny little number that we don't deal with really, but multiply it by 100 and we can say that 100 brake horsepower is equivalent to 74,600 watts or 7.4 kilowatts mechanical. And as we know, generators aren't 100% efficient. So when we want to convert that mechanical kW into electrical kW, it's not a straight shot. We've got to deduct a certain percentage for the efficiency of the generator. And these efficiencies, incidentally, are available from the generator manufacturer. They're not shy about this in their power curves. You can look, see what power you're taking, how many kW you're taking from it, and across from that, you'll see the amount of deduction that you have to make for the efficiency. Typically, it's between 92 and 95%. The larger the generator, the more efficient it is. So back to our engines. Spark ignition, small gasoline portables. Yeah, okay, moving on. Then we have the large gasoline engine derivatives of spark ignition engines. These are engines that the automotive industry are using, and they are produced in very large quantities. So there is a scale here that the more you make, the less expensive it is to make. So these engines tend to be very competitive. The automobile manufacturers will sell them to generator companies or others in short block or long block form. In other words, they don't have all the accessories on them which are needed for automotive duty. And the generator integrator will add the an exhaust system, a fuel system, and a flywheel housing, and make it suitable for a generator set. So those are good up to about 125 kW right now, with a turbocharged 8.1 liter V8 engine that is used on trucks. Above that, there aren't similar engines available, so we go to mostly diesel engine derivatives. And these tend to be more expensive than the original diesel engine because they've had to do some extra work to them to get them into natural gas formation. Just in case you know how a carburetor works, we've got a float chamber here and a little valve, a little float. And as fuel comes in, it tends to fill this up. This rises and shuts off the valve. There's a channel here where the gas can come through a nozzle. And as the intake air rushes in this area, there's a Venturi effect. The air velocity speeds up and it sucks the fuel from here. Then you've got a throttle. The thing about this is that the air-fuel ratio stays pretty much the same with the carbureted engine. The volume of the air and fuel mixture is regulated by the throttle or butterfly here. But more and more gas engines are actually running without a carburetor. They're being fueled by fuel injectors. So spark ignition mixes the air and the fuel before it gets into the combustion chamber, and the compression ratio is generally sort of 8-to-1 area. I'd say is probably the average. Now, compression ignition engine, on the other hand, it just takes air into the combustion chamber, and then fuel is injected directly. And the compression ratio of these engines is closer to 18-to-1. Actually, years back in the 70s, early 80s, Volkswagen came up with their Golf diesel, the first small mass production diesel car. That had a compression ratio of about 24-to-1, which was amazing, very high. And the thing about the diesel engine is it injects just exactly the fuel that's needed. So here we go again, folks. We've got two types of engine here: spark ignited and compression ignition. So let's just get clear about the advantages and disadvantages of both types. First of all, let's look at the advantages of the gaseous engine, the spark ignited engine. What are the advantages here?
Michael, can you repeat the question?
Yeah, what are the advantages of a spark ignited engine versus a diesel engine, or a natural gas engine versus a diesel?
Efficiency.
Probably not some. That's not a big one, because the diesel engines are the most efficient.
I think, how about power, right? The diesels provide more power output.
Yeah. Well, they're sized for the output that's needed, but throughout a pretty full range.
Or cleanliness of exhaust.
Yep. That is
Due to
certainly
the
an
fuel.
issue. Yep. Yep. With gas engines, you don't get the particulates. You have a little less NOx coming out of them. You tend to get a little more carbon monoxide, but okay. What about price? Where do you think they are there?
Depending on the size, I think these are a little bit cheaper, right?
Above a certain level, above 125 kW, they are less expensive.
Mm-hmm.
Okay, so here we go. Fuels, readily available. It's a fairly simple design. You may have a higher power density. Fuel consumption can be okay. Natural gas is always available. Lower cost up to 125 kW, more expensive after that. Replacement parts, generally lower price, especially on the smaller ones, the automotive derivatives. And you don't have on-site fuel storage. And that can be a big one.
Hey, Michael, I also have a quick question. So usually for, I think for diesel engine, right? So if you run it below a certain low, there could be causing like a wet stacking. So generally diesel engine works a little better in higher low percentage. But for these type of spark ignited engine assembly, I mean, are those able to actually work with a lower low without causing wet stacking, similar to how when we drive a car, right? I mean, when it idles, I mean, we could be sitting at traffic, not really driving, and those things still work. So that could be part of the advantage as well, right?
That's a very good point. And I'll be talking about wet stacking a little bit later on. But you're right in that natural gas engines do not wet stack. They can handle light loads very much better than a diesel engine. Diesel engines are designed to work, and they don't work as well when it's cold or due to low load conditions. So good point. As I said, I will be getting into wet stacking, and it does only apply to diesel engines. Okay, disadvantages of the natural gas engine. I really appreciate your questions, guys. Doing good. Why would you not use a natural gas engine?
How about the supplying of fuel,
Yeah, that's a good point.
storage?
Yep. Yeah, natural gas engines, the assumption is made that that pipe is always full of gas. That's not always the case. If there is a regional power failure, gas pressure may go down, gas pressure may be shut off. In some cases, some valves in the gas supply chain are electrically operated. Guess what happens if there's no power? It's shut off. So your generators, your natural gas generator set might not work. So that's, it's somewhat unusual, but it does happen. And that's one of the reasons why in some critical applications, such as hospitals and healthcare facilities, they require on-site fuel storage. So regardless of what is happening in the neighborhood or in the state, they will still have fuel available. So good point. Okay, what else? Anything else? Okay, I'll help you a little bit here. They're not as efficient as a diesel. And the reason is because of the compression ratio. Higher compression ratio, more heat, more fuel is burned. Part load efficiency isn't quite as good. Higher NOx emissions on some versions. We just talked about the fuel source. Low torque compared with a diesel, and higher fuel consumption than diesels. Now, if we move over to the diesel advantages, and just to be clear, I'm not selling either type. I don't have any skin in this game anymore. But there are advantages of both and disadvantages of both. We just want to identify them here so that if we have a choice in the future, we know the pros and cons and can make an educated decision as to which is best for a particular application. Okay, diesel engine advantages. What have we got here? There are a lot of brains out there. I know you're thinking, give me advantage of a diesel engine.
Well, we just talked about it being more efficient.
Yes, that's right. Yep, due to the higher compression ratio. Okay. And there's another one going back a few slides that we talked about on power.
Yeah, high torque.
Yep, thank you. Anything else? I don't have to read all these out to you. You can read just as fast as I can speak. you talk about durability and long service life. With one of my previous employers, an engine manufacturer, we had generator sets on remote lighthouses. We had 3 generator sets on each one, and one of them would be running continuously. We were getting 30 to 35,000 hours between overhauls on those engines. 35,000 hours between overhauls. Overhaul them and they're good for another 35,000 hours. Now, that's no benefit at all if you're running a standby generator set. If it runs for 2,000 hours, it's done its job, you know? Okay. Now, disadvantages on diesel engines. Let's have a contribution here.
Do they have a larger footprint?
Yes, they do. Yep.
And you got to deal with the exhaust issues, the dirtiness of the exhaust issues.
Yeah, it needs a little more equipment to meet the federal EPA requirements. Need exhaust after treatment.
The noise and probably the on-site fuel storage.
Yeah, they are noisier, and that's because of the high compression ratio. You get a bigger bang for your buck, literally. So they are noisier. You used to be able to tell, you can usually tell a diesel engine versus a gasoline engine on the highways. Actually, not so much now with the modern fuel injection systems, but they are noisier.
Is it difficult to find fuel for diesel engines?
Not really, except in a regional power failure. You know, if the utility is down and the gas stations and fuel suppliers can't get power to pump the fuel, then it could be an issue, which is why you have to have fuel on site. And there's another disadvantage is that there are some concerns of fuel spillage. I don't remember an installation where a diesel engine or diesel powered generator set actually spilled fuel because of the containment systems which they have, and basically the fuel tanks stayed intact. But anyway, that is a concern and a valid one. High vibration levels, again, because of the high compression ratio on the engines. They can be harder to start at extreme low temperatures. Because of the high compression ratio, you've got more mass of engine. They are heavier than natural gas engines, certainly below 125 kW, but they are fairly substantial. Okay, so we've got some advantages and disadvantages of both types of engine, and as I said before, there are places for both types. This might be something you folks don't have to worry too much about, because I think most of your installations are close to sea level. But if you're above 500, if you're above 1,000 feet, you need to be aware that the higher in altitude you go, the less oxygen there is for combustion, and therefore the engines are probably going to have to be derated. This is less of an issue with turbocharged engines. But if there's any doubt, then you can either go to the generator set manufacturer or the engine manufacturer or their distributor to find out if there is derating required for higher altitude. And now we get to discussing some of the basic engine parts that we've got. Got off the building block, which is a crankcase. So here we have an inverted V8 automotive crankcase, which would be used on 120 to, excuse me, 100 to 125 kW. This is upside down, and let me get my laser out here. So the crankshaft is going to go in this area here. here's another one the right way up. And here we've got 4 cylinders where the pistons are going to go. The crankshaft is going to go through here, and the camshaft is going to go through there. The crankshaft looks something like this. There are shell bearings. They'll probably have a steel back and copper lined. We're going to get lubrication to them. Lubrication is going to get forced through holes in the crankshaft. So we've got the main bearings, which are all in line and between each cylinder. So we've got one here, one there, and one over here. Usually you've got one more main bearing than you have cylinders. In reality, it's going to look something like that. And you can see the holes in the crankshaft here. This is for the oil supply. Oil will come into the main bearings, and then there's a hole that's drilled inside the throw here to the connecting rod bearings. That is a crankshaft, my friends. You even got a ladder to get down to the bottom of this area. This is the crankshaft from one of those 100,000 horsepower engines. Not quite, we're not quite in that league. But this is more our style here. So here you can see the crankshaft, the connecting rod, and the pistons. Here we've got a straight 4, here we've got a V8 and a V12. And where we have a V engine, we're going to have 2 connecting rods on the same throw, the same crank pin. And they can come in different arrangements, a single, a V-twin. That should be familiar to any motorcycle riders out there. 3-cylinder, 4-cylinder, straight 5. I got a 5-cylinder in my garage. A V5, which is really unusual. I think that was made by Volkswagen. They had one for a while. V6, V8, and then we can go up beyond that. On power generations, we'll find V10s, V12s, 16s, and V20s. One that's missing from here, which happens to be a personal favorite, is the straight 6. Very smooth. And with most engines, we've got the cylinders here, and the crankcase is made out of cast iron. So what most manufacturers do is they'll put a steel insert, the cylinder liner, in here. And then the piston, of course, goes in there. Here's the wrist pins and the piston rings, which fit around the side here, the oil control, and to keep the combustion in the combustion chamber. You can just make out at the top of this piston that it's generally flat, but there is a chamber here that is sort of scalloped into the aluminum. And that is the actual combustion chamber on a diesel engine. We'll have a gear train, and the thing we notice right away here is that the crankshaft down the bottom, and then we've got a camshaft gear here. I think that's a no, that's an auxiliary drive. We've got a camshaft up here, and the camshaft runs through there and operates push rods, but you'll see that this gear here is twice the diameter. And that is because we want the valves to operate every other stroke. With the 4-stroke, we've only got injection or combustion every other cycle. So we have to compensate for that with the camshaft. And you have to be very precise that we've got all the gears properly placed and in line. Then we've got some cylinder heads. Most engines today have 4 valves per cylinder. This is for greater efficiency. The easier the engine can breathe, the more efficient it's going to be. So we've got 4 valves per cylinder here and here. And you can see between the cylinders here, we've got, looks like a cutting, an opening here. This is for coolant to get from the engine block into the cylinder head and help to cool the combustion chamber. And over here, we've got a slightly different arrangement because here we've got the cylinder head for a 4-cylinder with a camshaft on the top. Overhead camshaft, more efficient than pushrod engines. And then we've got another one, which is a little bit unusual. Now, you might come to the conclusion here that these 4 holes, that 1, 2, 3, and just hidden over there, fairly large holes, these are for the hold down bolts. The bolts will go down there and to keep the cylinder head in place. We've got 2 valves for this cylinder, and we've got a hole here which will lead down to the combustion chamber. And I notice on this it's not threaded, so it's going to be a diesel. If it was threaded, then it would be for a spark plug. So what do you notice about this? Any ideas? What is this area for? It's not really a trick question, but it's not obvious. This is for an air-cooled diesel engine. Valves. 3 ways of operating the valves. This was the original one, the most, for a long time, the most common. You have the cam here, you can just see it's raised up here. So as this rotates, it pushes this push rod up, which pushes this up here at this end. There's a fulcrum point here, and that means it pushes this down against the spring pressure. Then we have an overhead camshaft arrangement here, somewhat similar, but the camshaft is on top of the cylinder head, and as a cam lobe hits this, it forces this part down, opens the valve. And then we have the most efficient of the 3, overhead camshaft operating directly on the top of the valve stem. So we do away with some parts on this. We do away with this mechanism and certainly the parts required here. So the less parts we can use, the more efficient it's going to be. The old KISS principle: keep it simple, stupid. And here's the arrangement. So we got the crankshaft bearings here, connecting rod, piston rings, combustion chamber here. The valves operated directly by the camshaft, which in this case is belt driven from the flywheel. Again, you've got a certain diameter here for this gear and double the diameter here, so this is rotating at half engine speed. Take it one stage further, and we could have a double overhead camshaft engine. Here we go. So 4 valves per cylinder and the appropriate cams here. Okay, how are we doing? Any questions? We will move along. So here we've got a single camshaft with a rocker arrangement, and it pushes down on this bridge, which opens both inlet valves at the same time, and on the other side, both exhaust valves are opened at the same time. In the middle, here we got a fuel injector with the electronic controls going to it. And inside again here, you can see the coolant channels, both on the around the cylinders, the top of the cylinder, and then in the cylinder head area around here. So piston rings, and here in the is a extra little squirt gun, if you like. This is squirting oil under pressure up to the underside of the piston to help cool it. On the other side here, with this other cylinder, you can see how this piston for a diesel is cut out for the combustion chamber. When the piston comes up to top dead center, there is almost no clearance between it and the cylinder head. Okay. See if I can keep up with this. Here we go. Engine assembly, crankshaft bearings, connecting rods going onto it. show you some pistons. Here they come. There's a wrist pin, clips that keep them in place. The other two pistons, we're putting a full cylinder together here, folks. Rotating it, we've got a little gear on there. Crankshaft bearings are going in place. So we're going to put it in the crankcase. There it is coming from above. Bolt those into place. Close that part of the crankcase off. There goes a camshaft. So this is a pushrod engine because the camshaft is way below. There are the valves, 4 valves per cylinder. There are the push rods on the right. And now we're going to bolt that cylinder head down in place. Valve springs, valve keepers. There they go. Cute. Then we got a rocker shaft and the rockers. A bit more of the cylinder head cover. And an EGR system going onto that engine. Now we've got the flywheel housing coming in. Oil filter, oil pan, fuel pressure pump, gear train, all coming together. End cover, bolt that in place. We got a fuel injection pump, manifold. There's a turbocharger. What's next? Controls, water pump, drive, a propeller, radiator fan. And we have reciprocation, a 4-cycle diesel engine. And the engines are always that clean, by the way. Okay, I mentioned EGR just now, exhaust gas recirculation. This is a system that many engine manufacturers use to reduce the NOx level of a diesel engine. And here's how it works. We've got, there it is. We've got intake air coming in from the turbocharger and the aftercooler. Comes into the engine for combustion. We have the power stroke, the exhaust stroke, the valve opens, and the exhaust is forced out by the piston into the exhaust system. But some of that exhaust is going to take a turn and come through a cooler. So we've got hot exhaust, we want to cool it down, and we're going to reintroduce it back into the engine. Now at that point, there is no chemical benefit whatsoever to that, or content, for that exhaust gas that's being recirculated. It's inert. It has no value other than the fact that it's cool. So it's exhaust that is totally spent. It comes into the combustion chamber, and it has the effect of reducing the combustion temperature and taking up a little bit of space. And in reducing the combustion temperature, it reduces the production of NOx. NOx happens, it's one of the chemical reactions between the nitrogen in the air and the oxygen temperature. The higher the temperature, the more NOx you're going to get. So this is a system to reduce the amount of NOx in a diesel engine and on a gas engine as well. You'll find these are on cars. So you know there's an EGR valve on your car. Looking at it a slightly different way. Here's the air filter. Here's the compressor part of the turbocharger. Comes through a cooler into the engine, into the combustion chamber. The exhaust comes out, goes through, provides power for the turbocharger, and goes out through the exhaust system, except for a little bit that comes out here. Gets cooled. There's a valve here to control it, and then it comes back and goes back into the engine. So that's how that works. Next up, we've got, yes, one of my favorite slides. Haha. I know it's not time to pull beers out of the refrigerator just yet, but when I see something like this, I can't resist it. I have to buy it. I'm an engine guy. I'm a gearhead. So old engine oil, 10W40, I'll buy it. And actually, it's not bad beer. But what we're talking about here is lubrication. Excuse me. Okay, so standard lubrication system, very similar to what's on cars. So you've got oil pickup here. It comes through pipe, goes into a channel, and here's the main oil channel inside the crankcase. And from here, it is distributed around the engine. It comes first of all into the crankshaft main bearings, and then there's a drilled hole that provides oil and lubrication for the connecting rod bearing. Some of the oil goes up to the top to lubricate any shafts and valves that are up there. So the purpose of the oil, of course, is to prevent direct contact between the rotating parts and the opposite piece of metal. So it's a spacer in a way, and it also provides some cooling, which is why we have it gets hot. So we cool the oil on many engines, and it also cleans the engines as well. This is why it has to be changed fairly frequently. Well, on page 27. Sorry, I'm having trouble advancing my slide here. There we go. Okay, there's a crankshaft in place. So it's important that we keep this oil clean, because there are going to be deposits from various parts of the engine, little microscopic pieces of metals, and so we'll put filters on there. All the oil passes through the full flow oil filter. On this one, there's 2 of them, and then there's and these will probably block any particles that are more than 10 microns in diameter. And then there's another one here, which is called a bypass filter. Not all engines have this, but this takes a certain percentage of the lube oil and puts it through a finer filter, which is probably going to be about 5 microns, and eventually all the oil will pass through this. And then we've got another filter over here, which is actually a coolant filter, which is a good idea to have. So, mentioned oil changes. Used to be 250 hours was the standard. Some engines are up to 500 hours between oil changes now. Truck engines, many of those are designed to go 100,000 miles between oil changes. So we have oil level makeup devices for an engine that's going to run unattended, or we want to be sure that everything is okay. And here's a very simple device. It's got an upper and a lower position, and if this float hits either of these, it's going to send out an alarm. Either your oil level is too low or it's too high. And if the oil level gets too high when it was set correctly originally, it means that something else is in there, either coolant or fuel. So it's a good warning to have on an engine. You can also have extended run systems, which I have some familiarity with, so that an engine can run for a certain amount of time. In our case, it was running 3 months completely unattended. No one there to check the oil system, and it's a pretty good and reliable system that we used. I got a car a couple of years ago, and being an engine guy, first thing I do is look under the hood. Okay, where's the dipstick? It's not there. They didn't put one on this car. What the heck? Because you've got to go to the control panel and the screen on the car, and there you can pull up various service items, and you can see what your oil level is. But they don't bother with the dipstick anymore. Okay, turbochargers. Always nice things to have, but they are put on to add more power, and they actually make the engine more efficient. Instead of that piston coming down on the induction stroke with the inlet valve open, when it comes down, it would create a slight vacuum. You know, it's working to pull that air in. With a turbocharger, air is being forced in. As soon as that inlet valve is open, we get a blast of fresh air coming right into it. So to produce more power, we've got to have more O2. more oxygen, and the turbocharger will give us that. Of course, the problem is that when we do that, when we compress that air, it's going to be hotter. That means for the same volume of air, we're getting less oxygen than if it was a lot cooler. So we put an aftercooler on the engine to cool the engine intake air between the turbocharger and the inlet manifold. And basically, we've got the exhaust coming out of the engine after the power stroke. It's forced through into the turbine section of the turbocharger. It spins this turbine wheel, which is connected to this shaft, which turns a compressor. And so the air that is coming in from the air cleaner hits this compressor, and it is forced under pressure into the engine. Because we have a much hotter intake air at this point, we put it through a charge air cooler, aftercooler, intercooler, whatever you want to call it, and then it goes into the engine. Much more efficient. In reality, this is what it looks like. So here we've got the exhaust coming up through here. It's a turbine wheel and goes out through into the exhaust system. So this turbine wheel is connected to the compressor, and here we've got the air coming in from the air cleaner. It's a compressor which forces it into the inlet manifold or through the aftercooler. So that's a turbocharger. And it occurred to me some time ago that if Rudolf Diesel could see this now, see what has happened to his invention of the diesel engine, we think he would be quite happy. He actually died a somewhat tragic death when he was traveling trying to sell his patents. He wasn't very successful as a businessman. He's a very successful inventor. But I think today he would be quite pleased with what happened. And at this point, let's take another 5-minute break while we can contemplate Rudolf Diesel. Okay, folks. Okay, so we've heated up the air through the turbocharger, and now we need to cool it. So there's 3 options that we've got, and these 2 here, the number 1 and number 2, aren't very often used. So I'm going to pass through these, but there are diagrams, as you'll see, coming up as to exactly how they would work. And so you can catch up on these if you need to. But the one I do want to mention is the air-to-air aftercooling. So simply put, we've got air coming in through the turbocharger. It's hot. We put it through an air-to-air cooler. So it's a little bit like a radiator, except that instead of coolant, we've got hot air coming in, and then from there it goes into the inlet manifold and into the engine cylinders. And what it looks like, and you've probably seen these, that here's the part for the water jacket right here. So this is the normal radiator, if you like, and then on each side we've got aftercoolers. So this is clearly a V engine with separate cooling, with two turbochargers and 2 aftercoolers. Here's another arrangement where you've got the radiator section here for the engine coolant and 2 aftercoolers, one above the other. The important thing is that the aftercooler is always the first thing in the airstream, so it gets the maximum cooling effect. And talking of cooling effects, we often refer to these engines as water-cooled engines. In fact, that's a little bit of a misnomer in my view. They have coolant in there, which is a mixture of water and other additives. Now we need certain properties in the coolant, which would be advantageous for the service of the engine, and we obviously want freeze protection. We'd like to have a higher boil point, so we've got a much wider range of temperatures in which the engine can operate at. It would be nice if we could prevent corrosion and scale from forming, and we don't want any cavitation with a water pump. So a good coolant will do that for us. There are several types. Alcohol-based coolant was actually used by Henry Ford, I think, on the first Model Ts. Not used anymore now, as far as I know. Ethylene glycol is the coolant of choice now. Propylene glycol is, it doesn't kill cats, so it's environmentally friendly. And then some engines are able to use an organic acid. There's a couple of other kinds of coolant that are used on engines, and if anyone can come up with what those might be, I'd be happy to tell. I'm not going to wait long for it, so if you know what it is, give me a shout. What other kinds of liquid can be used for, or what other kinds of coolant can be used on an engine? How about oil? Instead of glycol and water, you put oil in. There's a one manufacturer was producing an oil-cooled engine, and then there's air-cooled engines as well. So you remember that cylinder head with the fins on it? Cylinder walls were also finned, just like a motorcycle engine. The only problem with those air-cooled engines now is that it's difficult to get them through the EPA regulations. Here's another air-cooled engine. I think that's a Continental used on small airplanes. Various types of cooling fan are available. We'll go with a standard conventional. Actually, this is a kind of a neat design. It's designed to reduce the noise and be a little more efficient. Here we got more blades. This one can be is variable pitch on these blades. On some applications, on construction equipment particularly, you can reverse the flow with one of these, which is handy if you get a radiator that's blocking up with dust and stuff. You just turn the flow in the other direction. It'll blow all that dust back away. And then down here we've got an electric motor running a radiator fan for a remote application. And some engines will have an electric clutch built onto them, so it will turn on and off depending on the load on the engine. If the engine is cool, no need to run that fan. So we know that the freezing point of water, in other words, no ethylene glycol in here, freezing point is 0 degrees Celsius. And so we have no ethylene glycol in here. If we increase the content to say 20% ethylene glycol, then we're good down to about -8. Bring it up to 50%, and you see that we've got -37 degrees Fahrenheit on the Fahrenheit scale over here. So that is good for nearly all applications that we have. There's only a few installations where we need to do a little bit better than that, and you know, 65% is about as good as you can get, and that'll get you down to almost -60 degrees, which I wouldn't want to be in, frankly. But if you keep on adding more coolant, adding percentage, then in fact you're losing ground. So generally 50% is something everyone can remember, and that's a good place to be. Now we can affect the boiling point of the coolant as well. At no pressure and no ethylene glycol, it's going to boil at 212 degrees or 100 degrees C. Now, if we add the ethylene glycol, then we raise the boiling point up to 108. And if we pressurize it, then we can bring it up to 268, which gives us a much larger safety area. On the coolant system, same with most engines, whether they're automotive or for gensets, we've got the heat being developed around the cylinder block and the cylinder head, and that will go up to the radiator, pass through the radiator, and the air will cool it and it'll come back down and into the water pump. Unless the engine is cold, in which case this thermostat here is not going to allow the coolant to come up to the radiator. It will force it back down through this little channel here into the water pump, and it'll just recirculate the coolant until it reaches a certain temperature. Then the thermostat will open up and it'll be running as normal. So this allows for a much faster warm-up period. And that thermostat is a clever little device. So here's what it looks like. And this pin here is represented by this little shaft. And it is in an area of wax down here. So it's in this position normally, but then as the temperature rises, this wax expands and it forces this piston up, and that's what gives us the vertical movement on the thermostat. It's very simple, very reliable. And now we can go to an injector and see how that works, because this is kind of interesting. We've got fuel coming in. There's obviously a cross section of an injector. We're coming into this point here. Fuel is coming down in the body of the injector, all the way down into this chamber here. Now it's creating, we got this fuel coming in at pressure, okay? And it's being held in place by this spring directly above it. But when this pressure reaches a certain point, it will overcome the pressure of the spring. And what will happen is it will lift this nozzle up. And when it does that, it opens this valve and the fuel can flow directly through here and out through the nozzles. And the game here is to get the fuel under as high pressure as we can, so that the particles of fuel that come out here will be atomized. They'll be very, very fine particles of fuel, and that will ignite much easier. So that's how it works. And all injectors work on a similar principle. Let me show you, no, the device that creates the pump, that creates the pressure is a pump. And in this is the most simplest one here. The camshaft is going to come up and hit it and force fuel under pressure up through the top of the pump and into the injector. We've got a rotary injection pump here, does much the same thing, creates pressure in here, and the fuel comes out at the end there. With this one, we've got a camshaft built inside the injection pump. This is clearly for a 6-cylinder. And all of these little outlets here go to a separate pipe to each individual injector. And we can look at the system like this. Here's the injection pump going to the injector.
Folks, I know we have a 4-hour window here, but we do have about 15 more minutes. So we're going to try to, get through this. And if you have to leave, we understand, and you will be getting a copy of the recording.
Thank you, Nate. And this is what we see on most engines today. Instead of having a special valve and extra pressure, we've got the camshaft creating the pressure here, and with the ability to force fuel down to the injector nozzle. And the flow is controlled by the solenoid. So that was the most common form. But now we have the common rail system, which has many advantages. It's much faster, it's much cleaner, and much higher pressure. So we've got a fuel tank, and the fuel delivers down to a high pressure pump. And this high pressure pump will pressurize the fuel at a ridiculously high pressure, about 35,000 PSI. I mean, 35,000 pounds per square inch pressure to me is a little bit like the size of the national debt. You know, I just can't get my hands around that. But the fuel comes out at high pressure and comes around to, here's a common rail. And it's called a common rail because this rail filled with pressurized fuel supplies all of these injectors that are in the system. And the timing and the amount is controlled by the ECU, the engine control unit. So it tells each injector exactly when to inject fuel and how much. The pressure is already there. There's no waiting for it. And it reduces the noise and increases the efficiency. As I mentioned before, fuel is circulating around the injector. Not all of it is going into combustion. So there is a flow of fuel that is coming back into the fuel tank. Really cool system. I don't know if any engine manufacturers are up to 40,000 PSI yet, but it's probably coming. I think the most recent I heard was about 37,000. But when the fuel comes out at that pressure, I mean, you could almost cut steel with it. But it does come out as a vapor, so you get much better and more complete combustion. All designed to keep the engines as clean as possible. And here's what it looks like in real life. So there's your common rail and 4 injectors. And there's one with the high pressure pump. And then again. The other thing that happens with this common rail here is the pump is creating this high pressure. It will not allow greater pressure than what is designed for, and any excess pressure will be bled off into back to the fuel tank. And then here we go again. And that's kind of what combustion looks like. Now, I mentioned the ECU, the brains behind the whole system. This has been a game changer for diesel engines. We have a number of inputs: engine speed, governor position, water in the fuel, camshaft position, coolant level. I'll just touch on engine speed for a minute. That is controlled by a magnetic pickup. This device goes onto the engine on the flywheel housing and just a small, like half a turn off the flywheel ring gear, the starter teeth, if you like. And it creates a magnetic field, and it is able to count the pulses as the flywheel passes under it. And we also have these other parameters that the ECU is gauging the whole time. And with many of these, it will send out a pre-alarm to whoever is paying attention to it that the oil pressure is low and needs to be, someone needs to look at it. And then if it reaches a certain point, then it'll shut the engine down.
Question.
So we've got, yeah.
You mean the engine speed? This is the output and input, or just the input?
What we're talking here is just the engine. It's constantly monitoring the engine speed, the speed of the flywheel. So if there's any adjustment to it, it's going to send the signal to the governor, which will, in fact, in this case, it's sending the information directly to the injection system. And so it'll cut back on the fuel or increase the fuel so that it's maintaining that speed.
Oh, okay.
Okay, good.
Yeah,
Thank
you.
Thank you. Thank you. So those are the inputs. Here are the outputs, the fuel quantity and the injection timing.
Yeah, that's an item. Okay,
Okay.
sorry. Mm-hmm.
So both critical. You know, if one cylinder isn't doing its work, the CCU will sense it and will put more fuel to that one cylinder. It's very, very clever. And then we've also got diagnostics here, which is really handy and useful. I just mentioned the variable cam timing. So we can change the timing depending on what the particular cycle of the engine is and what it needs. And there's a feed of oil that goes into it round about here somewhere. Oil pressure will adjust it from one position to another. Okay, so apart from that, with the diagnostics, we've got any, oops, sorry, wrong way. If we got any gear heads here, you may remember that if you think one of the cylinders is a little bit weak on compression, you can take out an injector or a spark plug and put a gauge into it, crank the engine over it, and you can see exactly which cylinder is weak. Takes a little bit of time to do that, but now you don't need to do that. You can go to the laptop, plug it into the engine, and ask it to go to diagnostics, check compression. It'll rotate the engine several rotations without any fuel going in, and it'll give you a little graph like this. One of the cylinders will be at 100%, and all the others will be in relation to that. So if you've got one weak cylinder, you'll be able to see exactly which cylinder it is, and it'll take you just less than a minute to find that out. And you can also find the history of the engine as well. What fault events have been, you know, if there was oil pressure problems or whether it ran low on coolant at some point, it'll all be stored in there. And engine instruments and gauges. This is sort of old technology, if you like. There's still an awful lot of engines that have these analog gauges on them. So many of these gauges have pre-alarms to them and then shutdowns. Wide selection available, so you can monitor almost anything that you can put a sensor on. And then you've got a generator panel as well, which would typically looks like that, give you volts, amps, frequency, kW, phases, and all the rest of it. Today, we're going more and more digital, and we can get all the information on one panel, and you can transmit that information. I could have a generator set running in San Diego and be able to control it from here, from my desktop in North Carolina. I'd be able to look at the instrument panel and see exactly what the pressure was, what the coolant temperature is, what RPM it's running, how many hours are on that, and I could shut it down or start it up if I wanted to. So in case you have a loose generator end around and an engine that you could put it on, and you want to put the two together, the thing you have to make sure of is that you've got the right sizes on both. So here, this generator here, you can see the air comes in here, flows across the armature, and then you've got a cooling fan right behind here. So the hot air comes out in this direction, and the flywheel goes here. Now, the bolt pattern here goes onto the flywheel housing, and this part here is a flexible steel disc, and it goes directly onto the flywheel. So here's what we're going to mate it to. And we have standard sizes, so it's all very simple. SAE is the sort of governing body, if you like. It was SAE that developed this system and this standardization. So we have the flywheel housing here. It may be an SAE 1 or 0 if it's really big. or an SAE6, which would be fairly small, counterintuitive, I know. But that is the size and bolt pattern of this, the diameter. And then we got the flywheel in here, which has recesses, and you can see them cut here. It may have 3 or 4 recesses in there to suit different size flexible discs. And they're all well known. So again, it would be a 10-inch disc or a 12-inch disc, but it would be to a certain standard size. So knowing these, you can couple them up and you'd have a generator set partly built. So I'm going to finish in just a couple of minutes, but I do just want to show you this slide because it's a good place to finish off. So diesel improvements over the years, and particularly in the last 20 to 30 years since EPA got involved, we've gone to electronic unit injectors, variable valve timing, injection pressures. Used to be 2,800 psi when I first started. Now it's 35,000 plus. Multiple injections almost at the same time. Electronic management systems, those are game changers. And then we've got a number of other improvements that have happened. And in spite of dire warnings from manufacturers initially about what all these changes were going to cost and what it's going to do to the industry, the thermal efficiency has improved. I mentioned this before. Fuel consumption has improved. Exhaust emissions have improved. And it's the exhaust emissions that have been the driver of this, because the EPA regulations have required the engines to get cleaner and cleaner. And despite the engine manufacturers initially saying that they couldn't do it, they did. They got some very clever engineers, put their heads together and come up with some excellent solutions. So all these have been what they call the emissions strategy. So with that, it's just about 4:15. I think this is probably as far as anyone wants to go for today. So I will leave it now. Well, thank you for your attention. And not only that, but thank you for your input, your questions, and some very intelligent questions. And I appreciate the participation. It makes it easier for me when you all respond, and it makes it more enjoyable too. And we all learn a little bit more. So I will be talking with you again tomorrow morning. Tomorrow morning for you. And we'll talk then. So thank you, everybody. Have a good day.
Thank you very much, Michael. Bye.
Hello again, everybody. Good to be back. And sorry we had to cut short yesterday, but we will catch up and finish some important slides on prime movers before we starting. So I'm not going to rush this. If we're not finished starting systems by 4 o'clock Eastern time, we will continue the recording. And if you have to leave, that's fine. You will get copies of the complete presentation. So a quick refresher. We covered quite a lot of ground yesterday, actually, with the transfer of energy, and we went into prime movers and the different systems for prime movers. Now, one thing that we covered was fuel tanks, and a very good question came up from one of you, which I'm happy that we were able to find out. Underground storage tanks are regulated by the EPA and various other authorities as well. You can't just stick a tank underground and hope everything's going to be okay, because if you're found out, you will be in serious trouble. So there are regulations, and I've put a link down there to show you how you can get more information. But essentially, the underground tank has to be double walled. It has to have leak detection. It has to have corrosion protection. There's going to be inspections, most likely, reports, and as I said, state and local regulations may also apply in addition to the federal regulations. Tanks that are above ground generally have to meet UL 142 or 285, which will have many of the same criteria. As we discussed yesterday, they've got to be double walled, have leak detection, have enough capacity around them to contain at least 100 to 110% of the maximum fuel that's going to be kept in there. So I hope that answers the question that was raised yesterday. And it's fairly easy to get that information, by the way, just epa.gov, and then go to UST, which is underground storage tanks. Okay, so moving along. We discussed this yesterday, and it's a very important number, 746 watts or 0.746 kilowatts for 1 brake horsepower. So as I went through yesterday, 100 brake horsepower is equivalent to 74.6 kW mechanical, and there's some efficiency loss in the generator. So we have to take that into consideration. But the relevant question here, which may be important to some of you, is how much power are you going to need? Or put it the other way, how much generator power can you take from a particular engine? So let's say, for example, that somewhere on your base, you've got a 150 brake horsepower engine. And someone comes along and says, we need an extra generator. How much of a generator can we put on that? What's the output going to be? Well, the first thing you're going to do is to make sure that that engine is, in fact, a gen drive engine. It should have a flywheel housing on it that is compatible with the SAE specs. You may remember those from yesterday. So there's various standards available, and you want to make sure that it does have that SAE flywheel and flywheel housing on the engine. It may or may not have a cooling system on it. And there's a pretty safe bet if it's got an SAE housing on it, it'll have a governor that is suitable. But you should be able to get that from the spec sheets or from the engine serial number. So let's take this example here. 150 brake horsepower prime mover. What's the maximum electrical power? Well, the first thing we want to do is to convert that 150 brake horsepower into kW mechanical. And we do that by multiplying 150 by 0.746. And then multiply that by the generator efficiency. In this case, I've arbitrarily taken 94%. So that's 0.94. Multiply that out, and the math works out at 105 kW electrical is what you will get out of that generator by putting in 150 brake horsepower. So you're probably going to specify install a 100 kW or maybe 125 kW. It's usually better to oversize a generator a little bit than the engine. You don't want to oversize the engine for a particular application because you may run into that dreaded wet stacking. Let's do the reverse. Let's say that also in the warehouse somewhere, you've got a generator end. Let's say it's a 5 kWe generator. How much brake horsepower do you need to run that? You could probably do the math very quickly on your phones. You're just going to reverse that formula that we used above. So instead of multiplying everything by 0.746 and 0.94, you're going to divide the 500 by those two. And if you punched in the numbers correctly, you should end up with about 713 brake horsepower. So that's the size engine you're going to need to run 500 kW. All right. Now, of course, on engines, we have different ratings available. The manufacturer will give you the intermittent rating, the prime power rating, and the continuous rating. Intermittent is what's going to be used mostly for standby and emergency generator sets. That means you're going to be pulling maximum power only for a short period of time. Prime power is a little bit less than intermittent, usually by about 10%. And prime power is where you're going to be running the generator set as the sole source of electrical energy for this particular facility. There's going to be varying loads, but it's going to be running up to 24/7. Continuous is a little bit different because what we're implying here is that the engine is going to be running 24/7 at a fixed load. So that's probably going to be fairly close to its maximum. So that, again, is a little bit less than the prime power rating. There's no extra power available at the continuous rating. Now, Paul talked about alternator temperature rise, and perhaps Steve did as well, but these are the different temperature rises. And I'm not going to go into those, but what I will go into is the ratings for the generator set, which may or may not have been covered already, but here we go. Emergency power, as I mentioned yesterday, is the alternate source of electrical power for human safety and for the preservation of life. So those are very important applications, of course. Standby power is what most generator sets are rated at. And prime power, main source of electrical power, and continuous full power 24/7. You can double check on all those definitions on page 444 on your in your reference book. And now the interesting topic of dirty, nasty, ugly, smelly engines. And here's one. And then I'm not picking on Caterpillar, but this just happens to be a really good photograph of wet stacking. And what's happened here is we're looking at the exhaust side of the engine, and those pink things are the exhaust manifolds, and they're all joined together. They're sort of slipped it one into the next, and it kind of depends on the expansion of the metal while the engine is working to complete the seal. If the engine is running cold, then that seal is not going to be completed, and you will see some leakage down here along the side of the engine. And it's dripped down here and down onto this turbocharger pipe, but it's all a pretty ugly, nasty mess. And it's indicative of a fairly serious problem, the wet stacking. We know that it is caused by light load or no load at all. And the combustion temperature is too low for the combustion to be complete. So we have unburned fuel and oil coming into the beyond the combustion chamber. As a result of the cold temperature, the piston rings aren't expanding properly, so we don't get effective oil control. So we've got oil coming up the cylinder walls and into the combustion chamber. That makes the situation worse. We've got glazing of the cylinder walls, and this is what happens with a little bit of heat on that oil on the cylinder walls. It'll leave a film of oil, which is actually fairly hard. And that just causes the piston rings to slush up and down the cylinder without really doing what it's supposed to do. There's one other factor here which comes in. You can imagine when the engine is running on light load, there's not much flow going through the turbocharger. And what is going through is not enough to provide very much pressure on the inlet side of the turbocharger, on the compressor. It's not going to push a lot of air through there. So we're not going to get a lot of temperature on that coming out of the turbocharger. You know, normally, as I think I mentioned yesterday, you could expect 350 to 400 degrees coming out of the turbocharger. That's not going to happen on a light load. And it's compounded by the fact that after the turbocharger, we've got an aftercooler. So that cool air coming out of the turbocharger is going to get cooled even more. So we've got a double whammy here. So it's all a thoroughly bad thing. Now, we know that in most cases where we see wet stacking, the light load is actually caused by the automatic exercise cycle for the generator set. On standby generator sets, typically, they will run once a week automatically. It'll start up, it'll run for 1 hour, and then it'll shut down again. No load, because the facility doesn't want to transfer to the transfer rate of power. So this is a serious problem, and often we can't do too much about it. I won't say we can't do anything about it. There are some solutions. But one of the solutions is to, first of all, change that exercise cycle if at all possible. There's no point in running it every week, in my view. And what we've got coming up here are some personal opinions, to be honest with you. But I don't believe there's any benefit to running it once a week. The exercise cycle on no load purely tests the starting system of the generator set. And that includes the block heater and the battery. If those two are good, that diesel engine is going to start. I've seen diesels that have been sitting for a year and it'll start right away. Give it the heat, give it the fuel, and give it the temperature. It's going to light up. So testing it once a week is not necessarily is not a good idea. Running it is pointless. I see no benefit of that at all. All you're doing is making a bad condition worse. That exhaust with the particulates of fuel and oil is going to condense, and it's just going to get worse and worse. So I would recommend that instead of running it for an hour, run it for 15 minutes max. You've proved that the engine will start. What else can you do? You're not going to reach a normal operating temperature unless you've got load on that generator set. So that would be one recommendation. Here are the others. Put the engine on load if you can. If the facility can tolerate a 1 second blip on the power, then go ahead and put the engine on load when it's on its exercise cycle. Let it run the facility. That way you're not only testing the generator set, but you're also testing the circuit breakers, you're testing the transfer switch, and everything between the generator set and the facility. So if you can do that, that's the best way of exercising the generator set. You're testing everything. If you can't do that, then you can get the generator set load banked, and there is a section on load banks. I think it's probably tomorrow. But the generator set can be put under full load in stages up to 100% load, and that will clear out all the goop and nasty stuff that's in and around that engine. It'll get it up to operating temperature. So that is another solution there. And in some cases, it may be necessary to clean the cylinder. That's going to be a fairly expensive job. This is the penalty for leaving this bad situation too long. If you still get high oil consumption after you've cleaned the engine out, you're probably going to have to take it apart and hone out the cylinders. And that is basically using an abrasive wheel in the cylinders. This goes up and down and it cleans all the glaze off that cylinder, and you'll end up with nice shiny cast iron cylinders. And you'll have oil control back again, and you'll want to replace the piston rings while you're at it. Another option that you have is to install a radiator mounted load bank. So if nothing else can be done, it is possible and certainly a viable option to put a load bank in on the radiator section. So it will be air cooled, and it will typically have about a 30% load capacity, and that's enough to keep the engine clean. So when the engine goes through its exercise cycle or a no load period of operation, that load bank is going to kick in and give the generator some load. So that will keep it clean. If the generator is suddenly going online during an emergency, then of course that will shut off, and it's all automatic. You don't have to worry about it once it's installed. It's a more expensive solution than the others, but it certainly works. And in some cases, it's definitely beneficial to do that. And we don't have such an issue with the new engines because the fuel injection can be controlled a lot better. And one thing that is up on is that many companies are working on the probability of being able to shut off certain cylinders, because they can do that electronically now. It's fairly easy to do that. So if you've only got sort of 10% load on the engine, you would shut out a number of cylinders so that that load is being taken over by the 2 or 3 working cylinders. Okay, any questions so far? Okay, folks, if you've got any, write them down and come back to me. We'll move on to vibration isolation. This is something which applies to natural gas generator sets as well as diesel. Wet stacking, by the way, applies only to diesel engines. We do not have that problem with natural gas. So engines in power generation are reciprocating. They're going up and down, and during the start and stop of those engines is when you have the maximum vibration. So we invariably put vibration isolators under the generator set. I say invariably, if you've got a really solid surface, it is possible, and sometimes without penalty, to hard mount the generator set to the base. But 95%, perhaps higher, of generator sets have some form of vibration isolation. And there's different types available. There are hundreds of different types available, but the one that you want to be looking out for is down here on the lower right. This has the advantage of we've got springs here. So the springs will take the weight of the generator set and will smooth out the vertical nodes of the vibration. But we've also got this part is encapsulated within this frame here. So this will take care of and restrain the generator set during horizontal vibration. And what we're talking about here is, in the case of seismic activity. And here are two ways of placing the vibration isolators, either at each end of the generator set, one under the engine, one under the generator, and that goes directly onto the frame. Over on the right here, we've done it a little bit differently. And this is probably the more common way. We've got the vibration isolators under the frame. So the whole generator set is complete on top of that frame, on top of the vibration isolators. It does mean that it can be moved much easier than if you have to move this one out of the way. So, and you can see here, we've got the fully captive vibration isolators, and that provides pretty good insulation. In some cases, you know, with a smaller generator, it's easy to have a set pair each end and then one in the center. I always prefer to find out where the center of gravity of the generator set was and make that the central vibration isolation point. That way, each vibration isolator is taking an equal amount of weight. And wherever you've got these, every connection to that generator set has to be flexible, of course, because we are going to get some rocking and rolling when the generator set starts and stops. So we don't want any broken fuel pipes, exhaust pipes, and everything else is going to be flexible there. Another part that has to be flexible usually is with a ducting here that has to be a flexible stair if it's connected to the radiator. In many areas, we've got IBC, International Building Codes may apply, especially in the areas of seismic activity. Pay attention, guys. You will probably need these. Okay, so what's going to be happening in the future on prime movers? Well, here are just a few things that are going on. You can read these as well as I can, so I might comment on a few of them. Some of these are already in use. Solenoid actuated valves is an interesting one, and variable valve actuation. This will give us thermal control of the combustion. Start, stop, some of these come from the automotive industry, both commercial and private. Two-stroke engines, more about that in a minute. And a little bit more. We're seeing a number of different configurations coming into the market already. There's going to be a time, actually the time is now, when communication systems on generator sets mean that you don't have to make a frequent visit to a generator set. You can see everything that's happening to the generator. All on your iPad or phone. This just shows some of the advances that are being made right now. 4-cylinder 2-liter engine that'll go in most cars. Many cars have 4-cylinder 2-liter engines. It seems to be a standard size. They can now get 325 horsepower out of one of those. Okay, check this out. This is rather interesting because this is a 2-stroke engine, not 2-cycle, 2-stroke. So we've got a shaft down here, and you can see that it is down at bottom dead center. We've got 3 cylinders and 6 pistons. We've got a gear here which drives the gear at the top to another crankshaft, where we've got a similar arrangement as we have down below. And again, this is although it's at the top, it's really at the bottom dead center as far as its stroke is concerned. So what happens when the piston, when the cylinder, excuse me, let me get this right in a minute. When the engine rotates, the crankshaft is going to turn, pushing the piston, in fact, both pistons down. You'll notice that we've got holes in the cylinder walls here. I'll come back to that in a minute. So as soon as the pistons start coming closer, these holes are closed off because the piston is in the way. So we now compress the air, and the 2 pistons meet very close together in the center, which we would, in normal configuration, we would call top dead center. There's holes here for the injector. Now, as the piston comes close together, we can then inject the fuel, which will give us the power stroke. That will force the pistons apart, and that's rotating the crankshafts, plural. So the pistons are now moving back up, and as soon as they expose these holes here, we've got an air compressor or a supercharger that is forcing air in from the bottom, forcing fresh air in here under pressure, and at the same time, it's forcing the exhaust gases out through the holes in the top. That makes sense? So in one stroke, we've got fresh air coming in, the exhaust is gone, and we've now got a fully charged cylinder. Pistons come back together on the compression stroke, and we have the power stroke. And the compression stroke and the power stroke, those are the 2 strokes that we have on this 3-cylinder engine. Any questions about that? This is a fairly new design. Actually, the design itself basically goes back decades, but this is a newly designed engine, primarily for military use. On the left here, we have a new Fairbanks-Morse engine, and you that are familiar with electric boats, Fairbanks-Morse was the main engine that was used. Same sort of configuration, but clearly much larger. A posed piston, 2-stroke. And incidentally, I'd say that submarines were the first hybrid. Submarines go back, of course, back to the early part of the 20th century. And then the electric propulsion system came into effect with engines providing the recharging at the surface. Okay. So we talked about the learning objectives at the beginning of this session yesterday, and here they are again. So I would recommend that you take the time at some point when you have the time to go through these and make sure that you can answer these questions positively and without too much doubt. As part of this program, I've also got 10 important takeaways. I'm not going to go through those with you, but that is, those are some points that might be useful to you at some point in the future. And Nathan, that's the end of the prime movers, so we'll go straight ahead with